Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see a problem. 2493 divide the nodes into maximum number of groups. It has been asked by Uber and like quite a lot of times recently. Now, it simply says that you are given a positive integer n which represents the number of nodes in an undirected graph. Nodes are numbered from 1 to n. So you can see that you are given 6 nodes numbered from 1 to n. Okay. Next thing what they are mentioning is that you are also given some edges which represent simply the edge between AI to BI. And it's a bidirectional edge because as you can see it's an undirected graph and bidirectional edge which you have. Now they are also specifically mentioning that please make sure that the graph may be disconnected. What I mean by that is, okay, this is one connected graph, another can be there, another can be there. So you whatever answer you have to find, make sure you find it for this one, this one, this one, and add for all of them. That will be your final answer. Make sure you remember that because I actually missed it when I read in the very beginning. So now what is the operation? Operation is divide the nodes of graph M into M groups. What they mean by a group? Group is each node in the graph belongs to exactly one group. So it cannot be possible that this node belongs to two groups. As you can see, it only belongs to one group. This node belongs to one group. These two nodes belong to one group. These two nodes belong to one group. So each node belongs to only and only exactly one group. Now, for every pair of nodes in the graph that are connected by an edge, AI, BI, belongs to the group with the index x and bi belong to the y such that their difference is 1. It simply says that if you're trying to place them to groups, so for example you place them to a group 1 g1, then the next node, again when I say group 1, let's say the number is 1, right? The next number can be a difference of 1. It can be a 0 or a 2. So let's say, okay, if I place a 2, okay, and there's no other neighbor, so I'm good. For 2, if I have to place the other ones, obviously it should be having a difference of 1. Now, again, I can place a group 1. I can place easily a group 1 here. But will I place it? No, because I want to maximize my number of groups in which I can place. So I will try to have as many different number of groups as possible. So although I can place a G1, I can place these two nodes into G1, but no, I will not. I will take another group, G3. Again, because these are neighbors and neighbors should have a difference of group 3 minus 2, 1. 3 minus 2, 1. So neighbor nodes should have a difference of group of 1. This is exactly what they are mentioning. Cool. And then, okay, let's say for G3, this neighbor is 3. Okay, I will try to place it in a new group, G4. Here also, I have to place it to a different group. Now, obviously, for this G3, now you might say, Aryan, what shall I do? Can I place this to G5? Obviously, so like let's say if I talk about you, it is G3. So it can be either G2 or G4, right? This one then, like this person can also be G2 or G4. G2 already placed, so I will always try to place it at G4. G4. And thus, we realize that the answer for this is maximum 4 groups, and that's your answer. So, is it that simple? Like it seems like that, okay, I'm trying for a starting node and then I'm going on to the neighbor node, just putting up a group and then, going on to its neighbor node and trying to find all the possible variations. Not really, because if you go about that, okay, let's say if it is one group, then, neighbor can have +1, -1. So one node, other node can have two options, +1, -1. Then again two options, +1, -1, +1, -1. So you see, this can actually become pretty big and this can go to exponential complexity. Obviously, that would not work considering n. But oh, when I saw at n, I realized, oh, constraints are pretty low. There's some catch. Let's see what the catch is. But okay, so far we analyzed first example and we figured out this is how what they have found out, how they will place the group. Let's take the second example. Again, it's a second exact example. I will try. Let's place, okay, group 1. Next node I can place, obviously, I will try to place a group 2, group 2. But now I realize, okay, one thing. When I place here group 2, although, okay, this is first I placed, then because of this, I placed here G2 and G2. Obviously, now you might ask, Aryan, it is G2. Now for G2, the neighbor should have a difference of 1. So if it is G1, because of it, I let's say place another group G2. Now, because of G2, his possible candidates here at 3 can be a G1, a G1 or a G3. Because of G2, the neighbor can be a G1 or a G3. Because of G1, the neighbor can be a G0 or a G2. Oh, this says this make it as a G0 or a G2. This says make it as a G1 or a G3. Huh. I am not able to come to a conclusion what to make. Again, like, there is nothing common as what I can make. So, okay, I actually figured out that this will not be possible to actually make this third node to any group whatsoever, because if I place it to a G2, then obviously these two will be very mad with each other. If I place it to a G3 because of G2, then he will say, okay, I am neighbor, but my difference is not one. So, okay, I realized that this is something which causes an issue. So, what did you analyze from this? Okay, we analyzed that this is a cycle and this is causing us an issue. And specifically, a cycle of length 3 is causing us an issue. Oh, let's try that. Can we actually get this issue for a bigger length cycle? Okay, let's try for a length of 4. Let's take it if it is G1, group 1, obviously neighbor will be group 2. Again, so far everything is good. If it is group 2, the neighbor will be a group 3. And because it is a group 3, it is not connected here, thus it is happy. Oh, for a cycle of length 3, it was unhappy. Length 4, happy. Okay, let's try for more length. So let's say if it is G1, then neighbor will be a G2. Okay, happy, happy. Then for G2, obviously the next neighbor will be a G3. Here also, I can place a G1 or a G3. I see, okay, G1 is already placed. G3 is already placed. So I have to place something whatsoever. I can, again, let's say try if I place G1 or a G3. Now, if I place a G1, these two are still neighbors, but their difference is not 1. Oh, so obviously I cannot place a G1. Again, these two are neighbors, but the value is same. Not possible. There should be a difference of 1. Thus, I realize again, I cannot place anything. Did you see what exactly happened? Again, this is not possible. Did you see what exactly happened? You will realize that if you have something of this sort, that you are able to place, as you realize, you are able to place some group, then next group, then next group. Now, if I had some other node which can actually act as an ending node, which means a G4, then it was good. But if I somehow connected these two same group nodes, oh, it actually became an issue, which means an odd length cycle is actually an issue. Now, so your task, again, if you remember, the first condition was firstly find the maximum number of groups, but also return -1 if it is impossible to group the nodes with a given condition. So I simply realized if there is an odd length cycle, I won't be able to group the nodes at all. So if the question has odd length cycles, my answer will be -1. And again, if you don't know, to find out the odd length cycles, we have a simple concept of bipartite graph coloring. Again, I will do a dry run also of this, but if you want, you can just watch these two videos. Again, you can solve it by DFS also and BFS also. Okay, coming on back. So one thing we realized, okay, how we will find the answer for -1, which means not existing. Let's try to go and try to actually find the maximum number of groups, because your ultimately maqsad or target was to find the maximum number of groups. So let's go and find out that specific part. So again, but I mentioned that you have your graph may be disconnected. So make sure that you find the maximum number of groups for one component and then add it for all the components to get your final answer. So let's now focus on one component. Again, if you remember, this is the first example itself. Now for the first example, if you remembered, we took G1, then we went on to neighbors and put it as G2, then we went on to its neighbors, put it as G3, G3, then went on to its neighbors, put as G4, G4, and so on. Okay, but this is when I started my iteration from node 5. If you would have done it from any other node, let's say if I start from here, okay, then the neighbor is G2, G2, G2. Okay, then the neighbor is G3, G3. Oh, because when I started off from this node, my number of groups were 3. When I started off from this node, my number of groups were 4. Oh, which means it actually depends upon from which node you start. Oh, this is actually again an issue. Okay, no worries. But what we did? Let's say even if I tell you, okay, let's say you can try for every starting node. But if I say try for it, then the question is do what? Do what? If you look very closely what you did, we were on a node, we went on to its neighbor. We were on a node, we went on to its neighbor. We were on a node, we went on to its neighbor. So this is simply nothing but you were on a node and you did a graph traversal. Specifically, you are going on to the breadth-wise neighbors. That is the reason you can simply use a BFS here. So what I will do, I can simply use a BFS, and I can use this BFS starting from every node because I know the complexity n. N says 500, which means even if I run the BFS, BFS takes O of V plus E time. I have at max 1e4 edges. So still at max it will be 1e4, and I can run the BFS for all the nodes, whatever I have. And because of BFS, this will give me 4, this will give me 3, and I want the maximum, so I will take the maximum. So this is how I can find for one component running the BFS from every node. Again, I have n nodes, n into BFS, which is V plus E. E is 1e4, n is my 500, so it will be 5 into 1e6, which is pretty okay. So this is how I can go about it, running BFS from every node and then finding whichever, again when I say BFS, which means okay, running from here and then finding what is the maximum distance in this entire component, and then for that component that will be the answer. Okay, so you realize this is how you can go about it for one component and simply add it for all the components and get your answer. Let's do a quick dry run of all these steps. First step which you actually saw and found out was, detecting the odd length cycle. How will you do? Simple. This is based on coloring. Again, there are multiple ways to do it, but very simple ways coloring. How the coloring happens, that you have a color array in which you try to put it, because this is based on bipartite coloring. Bipartite says two coloring. So again, on the basis of whatever coloring you want, you can do any coloring, but let's say we usually do 1 and 2. And again, you can do 0 and 1 also. It's totally up to you. By default, you can put the values -1 and put the coloring as 0 or 1, or let's say 1 and 2. But again, that's totally up to you. So how we will do? Okay, let's say I represent my color array for the specific node 1 by some color. So in the very beginning, I will put the color. I will put the color as 1. Then what I will do? I will go on to its neighbors. I'll go on to its neighbors. And then again, by default, you will see that the color of all the nodes is 0. By default, I will put it as 0. Again, because technically you will see that you have to put some default value, right? So I'll put the color as by default 0. Then when I go on to the next node, I will check if its color is 0. Oh, yes. If it is, then put the color as, if it is 1, then put the color as 2. It is, I will put it as 2. How I did it? I simply said 3 minus current color will give me the new color. So 3, if the current color is 1, the new color will be 2. If the current color is 2, the new color will be 1. So that's how I found the next adjacent color. Same way here also, I found the next color, which is 2. Now, again, this is a simple DFS. So technically what will happen? You will try to go to all the neighbors. So for this one, you go on to next neighbor, which is you put the color as 2, but then you will also go on to this neighbor and you will put the color as, let's say, 2 here. And next iteration, what will happen? Obviously, next you will go on to its neighbor. You will see, okay, it's 0. Okay, no worries. Put the color as 3 minus current color, which is 1. So I will put it 1 here. And then from here also, if I would have gone here, I realize, okay, current color is 2. The expected color, although it is not 0, which means it is already visited, but also even after being visited, its color satisfies the condition. So I'm good to go. Again, more in depth you can find in the above video, link in description. Same way, let's say if I do a dry run for this in the very beginning, this color is 0. This color is a 0. This color is also a 0. This color is also a 0. And this color is also a 0. In the very beginning, I started off from the one color. Okay, 1. Then next, I will go on to its neighbor and will say, bro, your color will be 2. Again, as I mentioned, that you can do it via both DFS and BFS. So dependingly, whatever you want. In the code, I will show you a DFS approach, and the DFS simply says, keep on going. But again, logically, DFS also goes to neighbor. And when I say goes to neighbor, which means it knows it has to place a color of 3 minus 1, which is nothing but a 2. Okay, then as I am at 2, I will try to make him a next color, which is, color 1. And then, okay, no worries. With this also a color of 1. Now, this is done, this is done, this is done. Next, okay, I am here. I will say the next node. Oh, next node is already visited. But if it is visited, it should have a color opposite to me, which means if I have a 1, he should have a 2. So the color is not opposite. Oh, in that case, I am screwed up. This is actually a cycle which I have found. And that is how you can determine the cycle by using bipartite coloring. Okay, the next step, if you remembered, was if you have a bipartite coloring, you will have to go and run a simple BFS. But I also mentioned that you have to run this simple BFS from all nodes in that component. So once I will start off, let's say if I have this specific graph, so once I will start off my BFS from, let's say, one node and then another node and so on and so forth. But technically, my only target is, let's say if I started off my BFS from this node, then what is the maximum distance I can travel, or the maximum breadth, maximum depth in the BFS traversal I can have. That will give me the maximum number of groups. Same way, let's say if I travel from here, what is the maximum answer? So again, this is for one component. I am trying to have a start node as all the nodes of that component. So technically, you will have to figure out, which means that iterate on all the nodes of a specific component and do a BFS from that. Okay, let's do a BFS. Simply, I will have a by default distance array. Distance of 5, again, by default, everything is 0. So in the very beginning, the distance of 5 is 1. When I say distance of 5 is 1, which means technically I want to count groups. Groups is number of groups. Number of groups will tell me actually how many groups I have. That is the reason this represents one group. That's the reason I represent the distance as 1. Okay. Next, I will go on to its neighbor. Again, this is, as you know, it's a simple BFS. BFS is based on a queue. So 5, the neighbor is only 1. Okay. The distance of 1 will become a 2. 1 plus 1. Okay. Now, this is also visited. Next, go on to his neighbor, which is these two. So distance of 4 will become a 2 plus 1, which is 3. And same way, distance of 2 will become a 3. Okay, now these two are in the queue. Okay, for 2, go on to its neighbor, which means distance of 3 will become a 4 and distance of 6 will become a 4. Now for 4, which is inside the queue, he will see my neighbor is already visited. No worries, skip off. Which means that this told me if I start off from 5, the maximum distance achievable is 4. And that is okay. This is 4. But again, don't sit idle. Go and try for all the nodes of the starting node of this specific BFS. Here, the distance of 1 is 1. Then I go on to his neighbor and I will simply tell him that, bro, distance of 5 will be 2. Here, the distance of 4 will be 2. Here, the distance of 2 will be 2. Then in the queue, I have 5, 2 and 4. Okay, go on to his neighbor. 5, like no other neighbor is remaining because only neighbor was 1 and is already visited. How I will check visited? I can either take a visited array or I can take a by default distance value. If the distance is -1, okay, it is not visited. If it is any other value, it is visited. So, okay, for this, let's say 2, I go on to his neighbor and say distance of 3 will be 3 and here the distance of 6 will be 3. This gave me a maximum distance value of 3, but I want to maximize it. So I will take the maximum value for a specific component, which means I also have to figure out what is the component, right? Because I have to go to every component. So I have to figure out what are the nodes in that component itself. Now, for that, you can simply use either a DSU or a DFS. But technically, if you remember, I don't have to run, I don't have to at runtime attach nodes in a component. But still, you can solve it via DSU also and DFS also. But simply, I will use a DFS and will iterate through the component, get all the nodes of that specific component into a component vector. I will have a component vector and I will put, okay, 5, 1, 4, 2, 6, 3. These are the nodes of this component. Then I will run the BFS from all the nodes in that component, try to find the maximum distance that will be the maximum number of group of this component. And I will repeat this process for all the components and that will be my answer. Cool. Let's see the code finally. The code is simply very straightforward and simple as what I have told you. Again, I will show you firstly the corresponding, your bipartite code. Again, you can solve it by DFS and BFS both. You see that I will firstly do a default coloring of 1. Then I will put the coloring. I also am maintaining the current connected component because I have to get out all the nodes of that component, and then I will go on to its neighbors. Then I will check if the color of the neighbor is 0, which means it is not visited. If it is not visited, no worries, go and visit it. When I say go and visit it, which means go on to the neighbor and give a opposite coloring. Now, if it is already visited, which means if the color is not 0, then make sure the color is opposite. The color is opposite. If it is the same color, as you can see here, if it is the same color, it is actually not a bipartite graph. And this is how I can check if my bipartite for that component is true or false. So you will see this is, I have had a global variable, but this is for a component. As you can see, I am simply going on to all the nodes, and this is for a component. I place it at true and then call my DFS function. Again, this DFS is actually nothing but a bipartite. Just quickly, I will also show you that how I am finding in the BFS. BFS will simply get the maximum distance from a node. I will pass in a starting node and I will pass in that, okay, just do a BFS from this node, get me the maximum distance. A simple BFS simply pushes the current node in the queue, mark the current distance as 1. Again, make sure this distance represents the number of groups in a graph. And I also want to maximize the distance, right? So I will just say that, okay, start off from this node, which is a source node, get the current node out, go on to all of its neighbors. If the distance is -1, this distance -1 represents if the node is not yet visited. So if it is not yet visited, make sure to update the distance and also make sure to maximize your distance. Again, when I say maximize the distance, which means for the current component starting off from this source node, what is the maximum distance reachable, right? But you will see in my main function, I will do it for all of these starting nodes from a specific connected component. Cool. Let's go on to our actual main function. I simply firstly made sure that my color is set to 0. I made the corresponding graph for me. Then comes the final answer. Maximum groups. Maximum groups will be the summation of the maximum group of each component. Then I'll go on to each node. If it is 0, which means it is not yet visited. If it is 0, which means this component, let's say if this is, let's say one of the component, and let's say this is another component. Okay, let's say this is, let's say like this, and this is, let's say, another component. So these are, let's say, two components here. So if I'm going on to this node, first node, like this node, let's say this is I equal to 1. Then if the color is 0, which means that this component entirely is not visited yet. Okay, if not, then make sure that you put the connected components vector, because if you remember, I have this global vector which will maintain all the nodes in that specific connected component. So this vector, if I, let's say, number these nodes 3, 4, 5, 6 and 7, 8, 9, 10, 11 and 12. So what this will do, this is the vector which will store, again, when I will run the DFS, this will actually have all of the nodes in this connected component, which means it is a vector of 1, 2, 3, 4, 5 and 6. Cool. Then firstly, I will put the bipartite as true. Then I will run the DFS. This DFS will tell me, again, this has two functionalities. This will tell me firstly what all are the nodes in the connected component, and also will tell me if it is having a OR cycle or not. Now I will check if it is not a bipartite, simply return a -1, because if the entire graph has any one of the node having a OR cycle, I'm screwed up. If not, then find the maximum component distance, which means that right now in the current component I have nodes 1, 2, 3, 4, 5 and 6. Now run the BFS from each individual node. So firstly I will run the BFS from 1. So as you can see, I am running the BFS from 1 first. Then I will run from 2. Then from 2, then from 3 and so on and so forth. I will keep on running it, and whichever starting node of a component gave me the maximum reachable distance, I am simply maximizing that. And now let's say if I imagine, okay, 4 is giving the maximum. Okay, so 4 gave me maximum, but let's say whatever maximum distance it gave me, that is correspondingly my maximum distance. And this is answer for one component. I have to do it for all the components. So I will simply add it in my max groups and I will simply repeat this loop. Now, next iteration, when it will go to node 2, node 2 will already have a color, either a 1 or a 2, because it was visited in the previous step. So technically node 2 will have a color, which means it is already visited. So it will have a color, which means node 2 will have a color, node 3 will have a, node 4 will have, node 5 will have, node 6 will have, node 7 will not have. So now this for loop will come inside the inside this condition for the node 7, which is not yet visited. So you will see that because of this condition, right, because of this color, I am visiting all the nodes exactly once. Now for every node, or I should say every component I'll get the node and I'm running the BFS. Again, BFS in worst case can take O of B plus E time, but I'm doing it for all the nodes. Again, this is N plus E, let's say. So, but I'm doing it for all the nodes in the component. So this specific step is actually taking n into n plus e time. And thus, again, this will take O of n time only. But again, when I say n into n plus c, which is for all the nodes in this component, this is happening. Cumulatively, what is happening is that you are visiting all the nodes exactly once. So this is making sure you visit all the nodes exactly once. When you visit a node, for that node, the entire component is visited in one go. And when you visit the entire component in one go, this is that step which will make sure that for every node in the component itself, you are visiting its neighbors. Now, next time when you go to node 2, this will not be visited. So technically, you can feel this condition as for one component. This is one component. Like you are it because of these conditions, these two combined, you are visiting only individual components. So this is individual components for each component going on to all the nodes, which ultimately one, like it is each component. Each component has some nodes. So this combined will be a O of n, and for each component node you are doing a BFS traversal. That is the reason it will be O of n into n plus e. Don't confuse it with O of n into e. No, this is exactly how it happens. Now that's the reason the time complexity will be O of n into n plus e, which is nothing but O of n into e. And space, because you are simply using components and all that good stuff, graph and stuff. Okay, graph will have the corresponding edges, so the graph will actually be O of n plus e. Okay, mostly you are using guarded components as a vector, and all these things which are of size n. Cool. Because of this, your time and space will be time will be O of n into e, and space will be O of n plus e. Cool. I hope you guys got it. I hope you guys got the trident. I hope you guys got the specific part. Again, this is actually a very good problem. Notes and stuff can be found here, not right now, but probably in the future we'll have to we'll start adding it. LLD course starting soon. The structure for both LLD and HLD is already there. Again, no cap, already there. You can just go and check it out. Structure itself, if you like it, great. And we're starting off this soon in a couple of weeks. Bye bye. Take care.